On section 2.3, we were looking at doing the histograms. Histograms were a graphical way to show your relative or show your frequency distribution. The main thing that made a histogram different than two main things that made a histogram different than a bar graph. Histograms have to be having numbers. You cannot have it in different categories. So you have numerical values across the x-axis. Your y-axis is your frequency, how often it happened. Then the other major part was there are no gaps between it. That it's either in this section or it's in this section, and that part in the middle is going to be the boundary values. That number that is separating them is halfway between what would be in each one of them. So it's a number that you're not physically going to have possible, but it's going to, so it separates it into those different categories. Well, instead of just doing a histogram, we can also talk about a relative frequency histogram. The relative frequency histogram has the same shape and horizontal scale as a histogram, but the vertical scale is marked with relative frequencies instead of the actual frequencies. So we talked about the relative frequency distribution. Now we're just talking about that relative frequency histogram. Instead of having your y-axis tell you the number of counts, the frequency of how often they showed up, we're either putting it in percents, most likely, occasionally you'll see it in fraction form, but most of the time you're looking at it in percents. And so it's relative to the total amount that you're looking at. And so this one's doing the pulse rate in beats per minute. And so out of however many people they had, we're looking at how many of them had a beat per minute between the 59.5 and the 69.5. Again, you're not going to count 69.5 beats per minute, but if you count 69, it falls in this first class. If you count 70, it falls in the second class. So it definitely gives you that break of where it's going to be. And so the horizontal scale is still the exact same horizontal scale. And then these are just telling you that 30% of them fell in that first class. It looks like about 32% of them fell in the second class. And so it gives you those values relative to the total. Yes? Was it a two-pager? There was one assignment that was a two-page one. That also means... Okay, questions so far on relative frequency histograms? If we created a relative frequency histogram then for our groceries, so we had looked at how 50 people, 50 customers coming in, how much each one of them spent. We talked about making the relative frequency distribution last time, and since we were looking at having a total of 50 people, to figure out the percent that bought each group, so the percent of people that spent less than $10, we would be having 5 out of the 50. Well, 5 divided by 50 turned into a percent. Since it's out of 50, it's faster just to multiply it by 2. Means that 10% of them would fall into this. I better scoot those over because I'm going to need that number. So this will be 10%. This would be 38%. This would be 18%. So those are the same relative frequencies we looked at last time. If we were going to graph that one then, first of all, your horizontal scale is the same horizontal scale we had before. When you're doing this, you list your boundaries. That difference between $9.99 and $10 is 1 cent. Cut that in half, so it's half a penny. You add the half penny onto the upper boundaries. You subtract the half penny from those lower boundaries. And so we're going to go from the negative 0.5 to the 9. I better list them sideways. To the 9.995. And then the next one will be at the 19.995. So these are the exact same scale that we had across the bottom last time. It is. Thank you. Yeah, half penny, not 50 cents. Oh, and I don't know why I didn't start. That should have been here. Should have been this one. I'm just going to scooch it over though. Oops. I should have had my scale start at that one, and I don't know why I didn't. So now, as we go through and do these with that relative frequency, having our horizontal scale is no longer going to be the count that you had, it is the percents. Since our percent needs to go up to at least 38%, 5s won't work, 10, 20, 30, 40, 10s will. And so this one's your relative frequency that we're putting in here. And then just graphing them the same way we would have before. We had the first one was at 10%, the next one went on up to 38%, 18%, the next two, 6%, 2%, and 8%. Oh, darn it. So it should have looked something like that. Now, the shape is going to be the exact same shape we did when we did the frequency distribution. So it just changes that horizontal, or that vertical scale is the only thing that would have changed. Honestly, if we would have been counting on this one, we would have counted if it was doing the frequency. Pick a different color. This could have stood for 5. This could have been 10, 15, and 20. And notice that they would have had the same values. And the reason I'm doing that is because to get from 5 out of 50 would have been your 10%, so going backwards. It would have had the exact same shape as we're doing this. All we're doing is changing that vertical scale to make it a percent so it's relative to all the rest of the values. Questions on doing those? Keep in mind, when you talk about a relative anything, it means it's in comparison to everything else. So this relative frequency histogram means it's in comparison to all the rest of those. So you'll either have it, it's the same thing, you'll either have it as a percent or as a fraction when you're talking about those relative frequency distributions. If you're trying to interpret it then, the objective is not simply to construct a histogram, but rather to understand something about the data. When graphed, a normal distribution has that bell shape. And so the characteristics of your bell shape, and it's going to have that kind of a distribution is your bell-shaped distribution, your normal distribution. The frequencies increase to a maximum and then decrease. And their symmetry with the left half of the graph is roughly a mirror image of the right half. And so a lot of things naturally occur. If we were talking about heights of people and counting how many people were in each of the different classes of heights, it would have a bell curve. That you've got a lot of people that are about the same height. You've got some people that are shorter. You've got some people that are taller, and it fits pretty good in a normal distribution. So it has that bell curve as you look at those, where you increase until you reach that maximum, and then you kind of decrease back, and that should have a nice reflective pattern to it. This one that we did, I guess actually let me back up to this one. This one we did was not really a good normal distribution. It was definitely skewed. You went quickly up to the maximum amount, and then it slowly tapered off. You cannot draw a line down the middle and see any kind of symmetry between these. So this one would be skewed. It's moved off to one side or the other. This one's called a right skewed distribution. This one is an example of a good normal distribution. When you talk about a normal distribution, if you're talking about things that happen in real life, it's not going to be perfectly fitting the exact pattern that we want it to be. So you're not going to have a perfectly normal distribution, but we can see that it increases and then it decreases. So we've got that maximum amount in the middle. It's got a pretty good symmetry that your most amount is here in the middle, and then it decreases from here and decreases, and it kind of keeps working its way out. It's not perfect. It's not exactly 178 and 178, or 251 and 251 on both sides of it, but you can see that it kind of fits that pattern. And so this one would be considered a good bell-shaped distribution. And so you can see that from the histogram as we're putting things into those different classes as far as what we get. And notice on this one, I want to point out their scale across the bottom. They did the scale first, and then they plotted things. They're not showing exactly where each one of their different breaks are at. They've got their scale first. A lot of times you'll see things with just having the original scale. When you guys are doing things, I want you to show me the boundaries. So I want to know what is the upper and lower boundaries when you guys are graphing these. If you're trying to use the calculator to do the histogram, which is one of the things you might not do as often, that a lot of times it's a little easier to go ahead and do those by hand. But if you were trying to look at a lot of data and you're trying to see what kind of general shape does it have, so you've already got the data, you're going to be doing some other stuff with it, so you're going to be putting it in the calculator anyhow, trying to figure out what it's going to look like. Do I have data? Okay, I've got some data in here already. So if we were using these, oops, let me zoom in so you can actually see what I'm doing, sorry. So having that data, so I've already put it into list, oh, wait a second, I don't even want to put it just all into there. We're just going to put only the numbers into list 1. Let's say we were going around and just taking ages of people, and the first person was 18, we had a 19, we had a 20, we had a 22, we had a student that was 35, we had another student that was 18, another that was 20, and one that was, I don't know, we'll go 21. So if those were students' ages that we were looking at, and we were trying to make it into a histogram, so you put the data in there first, and then you're going to go to, and you're just putting that in that first list. Go to stat plot, which is right above the y equals, and we're going to turn that plot on. We're going to select that we're wanting it to look kind of like a bar graph because it is a histogram that we're doing. Your values are coming from list 1. The frequency is just telling you how often is it going to pick that value. Now to make it graph, we're going to go to zoom, which is across the top, and we're going to go down to zoom stat. So it's saying it's going to graph the statistics that we had, so it's making it scale appropriate for our statistics. I hope I put too many people in the same age brackets. To see what you've got across the bottom, if you hit trace, so if you just hit trace, it's going to tell you what your values are. It's telling me my value is, the minimum is 18, my maximum is 22.25, and there's 7 people in that group. Then we have a bunch of zeros till we jump out to the person that's 35. I'm going to change my data. 35-year-olds kind of making us really stand out really badly. Let's do a 28-year-old. Let's put a couple more people in the middle. So now I can just go to zoom and do number 9 as stat plot. And it kind of spread it out a little bit better for us to be able to see. And again, you can just hit trace to see how many are got falling into each of those different categories. And it broke it up a little because now that first class only has 5 people in it because it went with the minimum of 18 to a maximum of 20.5. Now, it won't break it into a lot of different classes, but a lot of times it gives you a good idea. You can definitely see this is not a nice normal distribution, that we have a lot of people that are younger and very few people that are older, so it's not a normal distribution, but it gives you a way to visually quickly see if it looks normal or not. Questions there? Turn it to where you guys can see things. All right, that finishes up section 2.3 then, with working with the histograms. Now I want to go ahead and look at section 2.4, which is looking at different types of graphs. So your histogram is one kind of graph that we can use, but there's lots of other ones that we can look at too. One of them, and some of these are going to be ones you're very familiar with, some of them are ones that you're not familiar with at all. One of which that you're probably not as familiar with is your frequency polygon. This is uses line segments connected to points directly above the class midpoint values. So this is very similar to your histogram, but instead of using the bars, we are going to use the lines connecting things, and they're going to the class midpoints. So if we were looking at this one, also notice that when you do these, they always go back to your axes. So if you're talking about a frequency polygon, everybody's included. You're not going to make a histogram and just leave off a few because you didn't like their values. All of them need to be included in there, so we couldn't have ignored our 35-year-old in our ages that we were just looking at. We'd have to include all of them. So we're connecting the class midpoint. So if you were to turn it back into a polygon, we'd be going halfway between each of these values, preferably making straight lines. So we could turn this one back into a histogram. If we went around each of those, because each of these are those class midpoints. You're taking the middle values and connecting each of those. And then you're just doing your frequency on the side. So your frequency polygon is going to always connect back to the x-axis. And you're connecting all of the class midpoints. It's a polygon because it kind of looks like it's a polygon when you're done with it. We could also do relative frequency polygons. Big difference between a frequency polygon and a relative frequency polygon would be what? We're changing it into percentages. We're just changing what we put on the y-axis. And so now that we're looking at these, again, we still connect them back to the axis. And is where that next midpoint would have landed if you were to do those. So that you're continuing to keep that same shape going on. This one makes it easy to compare the men and the women. That we're talking about pulse rates. So you can graphically see pretty quickly that you anticipate men to have a lower pulse rate than women. That's where most of the values are landing at. You can see that women have kind of a normal distribution, but it's a little skewed because you're getting some people that are way out here at the very end, and we don't have any that are really low pulse rates. So it's not exactly a normal distribution, but it gives you a good shape of what things look like. But again, you're connecting the class midpoints of each of those. But your vertical scale is just the percents. The ogive is one that you probably have not seen before. The ogive is a line graph that depicts cumulative frequencies. Cumulative means we're continuing to add them up, so it's going to continue to increase the whole entire time. If it ever dips down, that tells you have not done a cumulative frequency distribution. It's not an ogive. That it has to continue to go up. So this last value over here, that's going to tell you the total amount that have that were in their group. They're in their sample that we're doing of people with pulse rates. So this is telling me since it went up to 40 that there were 40 people in their sample that they were finding the pulse rates of. So you're continuing the first group, and again, this is connecting those class midpoints as we do it. So in that first class, it looks like we had about 12 of them. Combined, we're all the way up to 26 of the values are less than that 79.5. And so we've added both the 12 and the 14 that would have been the next class. And I think I said that backwards. These are not going to the class midpoints. These are going to the upper boundary because you are looking at the ones that are going to be less than those values as you're making that ogive. But again, your numbers are always increasing as you do that one. Another one is a dot plot. Your dot plot consists of a graph in which each data value is plotted as a point or a dot along a scale of values. Dots representing equal values are stacked. One of the key things you're doing, this is kind of a way to organize your data. If you were getting thrown all of the numbers of how many people were in each class, we took the ages of everybody in, all of my classes. So you took 100 students or so, and I gave you everybody's age, you're not going to want to go through and just count all the 18-year-olds and then count all the 19-year-olds because it's easy to skip one as you go. So the dot plot is a good way to help you organize your data. So this is talking about the pulse rates of females. So each time somebody came in, they just put a dot when they measured their different pulses. And so it helps you organize that information. Keep in mind when you're doing these, each dot represents, in this case, each person that we're looking at, each data value you get. You have to have a scale first. Anytime you're making a graph, have your scale first. Don't just go with the numbers you get. So we had somebody that had 60, then a 64, that looks like a 68. We get over here, it looks like we have an 88. Before you were having things every 4. We don't have a 92, but you still have to include those kind of values in there. You can't just skip them. You can't just skip from having 96 to 104 to 124, to where you don't have a consistent scale. Make the scale first. They counted by 5s first, and then they put their values where they belonged. Having the scale first is very, very important. If you guys go with giving me any kind of graph that does not have a scale that's counting by the same numbers, I will count it wrong, because it doesn't help you to visually see anything if you don't have a scale first. So don't skip any numbers just because it's a pain to have to go all the way out to 124. You don't just bring him over closer just because you don't want to count that far. Questions on the dot plot? Another one is the stem plot. A lot of times we call it a stem and leaf plot. This represents quantitative data by separating each value into 2 parts. The stem, which is the leftmost digit, and the leaf, which is your rightmost digit. A lot of times that's how you're going to look at things. So if we look at this one, what's great about the stem and leaf plot is that you keep all your original data, but you still have a way to compare things really easily. This is saying these are the 10s digits, these are the 1s digits with my leaves. So we had a person that was 60, another one that's 60, 60, and then we went up to 64. So we still have all the original data. We can see that the highest pulse rate was 124 beats per minute. And so that's giving me my original data, but it's kind of like the dot plot as far as it's helping us really organize and put things together. It is helpful when you do a stem and leaf plot if, like they did, you have your numbers in order. If you're creating the stem and leaf plot because you're taking all the original data and you're looking at, writing down people's ages, and you're going with each decade being its own thing, and you're looking at how many 18-year-old, how many people were in the, so you'd have your 18s that you'd each write down, and then you'd write your 22, and you'd write whatever my numbers were that I had. Having each one of those getting written down in your stem and leaf plot kind of helps you organize stuff. But that's especially helpful when you've got your data pretty widespread, where it's covering multiple digits it would be using. Questions on that one? I'm trying to remember if I had any examples that I wanted to show yet. I think they come in a little bit. If we looked at page 47 and we made our own stem and leaf plot, so if we did this for the pulse rates of females, the other one was the pulse rates of males. First of all, what would I need to have for my stems? Okay, my lowest first number is, I don't see anybody in the 50s. My highest one is, okay, so it looks like we go up to 124. Well, that was, let's do males. That was females last time. Let's go say that 124 showing up again. Let's do males instead of females. So let's do the males. What's the lowest male value we see then? See males in the 50s. What's the highest we see for the males? Okay, so we just have to have our stems cover from the 5s all the way to the 9s. And then you just go through and you start looking at them. So the first male was a 68, so we would put our 8 in here. Next male was a 64. They don't have to. Preferable, especially if you're actually going to display this data for somebody else to see later, you would want to reorganize it. When you're first helping yourself and figuring out what you're doing, It's just a matter of writing in what we had. So that next one would be the 72. Also, try to keep things kind of evenly spaced. Don't put some of them really, really close and then spread others really, really far out. I'm going to give you guys a minute to finish doing a few of those. Just do the top line. Don't worry about the bottom line yet. So just taking that data from the top one, you can see that it's hard to tell for sure on this one whether or not it is a normal distribution, because the top number, the biggest values in the 60s versus the 70s and 80s, if we were looking at normal distribution, we would hope that the 70s would be a little bit higher. We've got a really small sample though, so it's really hard to tell, but it looks like it's leaning towards having a normal distribution because you definitely have the larger amounts in the middle, and it looks pretty even on both sides. So it's close to a normal distribution. We'd really need to see a little more data to decide on that one. But any questions on what we're looking at with the stem and leaf plot? Bar graphs. Bar graphs use bars of equal width to show frequencies of categories or qualitative data. So your quantitative is when we have numbers. Qualitative data is some sort of other way of describing this information. Your vertical scale represents the frequencies or relative frequencies. Your horizontal scale identifies the different categories of qualitative data. A multiple bar graph has two or more sets of bars and is used to compare two or more sets of data. So bar graphs are things we're all pretty familiar with. This would be a multiple bar graph where it's looking at the median income of males and females. And so the blue is the male income, the orange is the female income. But comparing this one, even though it is counting by the years, we're not showing data for every single year. As they're doing it, they're jumping from 1950 to 1960. So it's not taking from 1950 to 1960 and finding the average mean in that time period. It's saying this is what it was in 1950, this is what it was in 1960. So you cannot put those side by side because there is space in between those. It's not showing us what it was in 1951, and 1951 is not incorporated into that data. And so since that's not, this is a good example of using a bar graph. On this one, you can definitely see that the median income of males has increased drastically from the 1950s to 2000. It's also increased drastically for females. Trying to use different ways of comparing this. Some people can use this to be able to try to show how males have increased more dramatically than females. Other people can take this data and be able to talk about how females have increased faster than males have increased. It depends on how you describe your data. That's one of the things that we'll be looking at as we go, is looking at that description. Because as you look at these, going from 1950 to 1960s, you can see that women, looks like more than doubled their income, where men did not double how much more they made during that time period. But you can also see that the gap between a male and female grew from 1950 to 1960. So there's different ways to describe that data, and understanding that there is more than one way to describe it is an important thing to be able to look at. And that's part of when you're reading information about graphs, is the skew that the person who wants to show you that information can slant that same information, that same data, different ways depending on how they want to say it. A Pareto chart. A Pareto chart is a bar graph for qualitative data with the bars arranged in descending order according to frequencies. For graphing a bar graph, this one's talking about different ways that people got their jobs. And so it's the percentage of people that got their jobs through networking was over 60%, through a newspaper ad, internet, application in person, employment agency, and through their school. And so looking at the different ways that this sample got their jobs, well, putting it in order made more sense. There's not anything that just in general that would say networking is better than newspaper is better than internet, and this is the order that it has to be. Because if somebody else put this in a different order, that would be okay. But when you do the Pareto chart, you are putting it in descending order. Kind of like if we were to try to take a survey of people, the types of pets that people like. There's nothing that says a cat is better than a dog, is better than a fish, is better than a chicken. So there's one right way to be able to say what kind of pet you're supposed to have. But if you were doing the Pareto chart and you found that most people had dogs, then you'd want to put dogs first, and then more people, the next largest category was cats. Then the Pareto chart would say you would put that in a certain order to have that in descending order. And it makes it easier, especially if things are close. If we separated quite a ways the amount of internet compared to the application in person, if one of them was at the very beginning and one of them was at the very end, it would be hard to tell from a distance which one's better. Putting these where you're putting it in descending order makes it real easy to tell which one's better and which one was how close they were and different things like that. Now, pie charts is a type of graph that you see frequently. Pie charts you have to be very careful with. We're going to talk, I think, next time. We get to talk about misleading graphs. Pie charts are a lot of times a misleading graph. Pie charts are a graph depicting qualitative data as slices of a circle. The size of a slice is proportional to the frequency count. So because most people got their jobs by networking, networking took up the biggest piece of the pie. The problem is, and we'll talk more about this next time, when you look at these, which is bigger, internet or applied in person? Does the little orange, the light orange or the blue look bigger? Okay, light orange looks a little bit bigger, but it's kind of hard to really just glance at it really quickly and tell, well, how much percent bigger is it? Back here, applied in person compared to the internet, it's real obvious to see that the internet was better than the applied in person. So to be able to look at the pie charts, it's hard for people to visually calculate out what that percent difference was, what those areas were. Now, if I had to do this by hand, and I know anymore, most of us, if we were having to make a pie chart, we would use some sort of graphing utility. We'd use probably pull it into the computer, type the stuff in, and let it make the pie chart for us. But thinking through what you have to know. How do we calculate stuff out using a pie chart? I don't remember if I have it on the slide or not. Nope. If I was trying to calculate out the pie chart, let's say I interviewed, let's go with 20 students. I guess I can't do interviews. That wouldn't be a good idea. Because when you're doing a pie chart, you have to have every single person that's in it. So let's say let's pretend I had 20 students in a statistics class last semester. And out of the 20 students in the class that we had, have 8 of them that got an A, 5 of them got a B, 2 of them got a C, 4 of them got a D, and 1 person failed. Is adding up right, doesn't it? 10? Yeah. If that was accurate, which it's totally made up, but if that was accurate, how would I figure out what slice of the pie we needed to have for the A's? Okay. So, yes, you're correct. I'm going to go a little different. Because most of the time when we do this, we talk about the percent. What percent of my students got an A? How do you figure out what percent had an A? Okay, 8 out of 20. So if I take 8 divided by 20 and then change that from a decimal to a percent, what do you guys get? Okay. And since I made it out of 20, it was an easy one to do in our head. To get to 20 to 100, you multiplied by 5. So 8 times 5 gave you the 40%. How do I change it from 40% into how many degrees it needs to be? And that's where what you were saying, Shelby, was important. How many degrees in a circle? 360. So what is 40% of 360? Okay. And so we would need to have that one be 144 degrees. And so you would find your spot. So you'd first have yourself a circle, having that center amount. From that line, we would measure out 144 degrees. So where that would be 144 degrees, and then that would be our percent that would have the A's. And so then we would go through and measure out the rest of those. But being able to convert it from the quantity into the percent into the decimal amount would be an important piece that you'd have to do. Computers do a lot of that for you anymore. But recognizing what it's doing so you can go back and check to make sure it's accurate is important too. But the only time you can use a pie chart if you know 100% of the values. If we were talking about the different types of ways that people got jobs, if there was any other job or any other connection method that they had, we could not have made this into a pie chart. They had to know every single possible way that those people found a job. And there also couldn't be any kind of repeats. They couldn't say, well, I did it through both networking and applied in person. It had to be one or the other. They had to just select one as you did this. Okay, a scatter plot or a scatter diagram is a plot of your paired data, so it has to have ordered pairs, x and y, with the horizontal x-axis and a vertical y-axis. It's used to determine whether there is a relationship between the two variables. This one is looking at crickets and the amount of chirps per minute compared to the temperature. And as they were comparing this, and so we were looking at a cricket was going, let's see, I'm trying to read what my numbers are here. It looks like that's at about 880 chirps per minute when it was 70 degrees, compared to when there were 900 chirps per minute when it was about 81 degrees. And so each of those are paired data, that those two pieces went together. Is there any kind of pattern that we look like we're seeing? Warmer the temperature, the more chirps. And so it's an old method of doing things, of trying to help predict the temperature just based off how much you're hearing the crickets chirping. And looking at the pattern, that we can see that there is kind of a pattern, that it is increasing. And so being able to look at the different data presented different ways shows us stuff. But this has to be that paired data, where each piece has to go together as a pair. Another one is your time series graph. Data that have been collected at different points in time would be your time series data. So if every year, and this is the Dow Jones Industrial Average high, so looking at what the high was in 1980, and then 1981 and 1982, where each year we're looking at that value and looking at that comparison over time. So it definitely would not be, you'd have to have some sort of way of recognizing what kind of time period you're talking about if you were trying to look at things going on with the Dow Jones Industrial Average highs. Because you can definitely see that there's a pattern, that it's been increasing most of the time from 1980 until 2005, with a dip in there, but that we've had that general pattern of increasing as things have gone on. And that is definitely some data that you see in the newspapers on a regular basis. It's your different kinds of time series data, where this one's looking at Kansas City regional stocks and looking at how the stocks change throughout the daytime. So it's not just only looking at over years. This is time of day and what was going on with those stocks. When we're graphing, if you look at page 66, So trying to decide whether to use a graph or not and what type of graph to look for. When you have small data sets of 20 values or fewer, use a table instead of a graph. Because the graphs are trying to help you organize a lot of information. If you don't have a whole lot of information, if it's less than 20 things, then a lot of times just showing those numbers, showing them organized in their graph or in their table is much easier to use. A graph of data should make the viewer focus on the true nature of the data and not on other elements such as eye-catching but distracting design features. And we will look at inappropriate graphs and stuff like that next time. And so paying attention to making sure that you are not trying to distract from the true information is important. Do not distort the data. Construct a graph to reveal the true nature of that data. So we talked one time about, and we'll talk again next time, not always starting at 0 on your vertical scale, and that can be a distortion of that data because it makes it look like there's a bigger change than what there really was. Almost all of the ink in a graph should be used for the data and not for other design elements. Don't use screening consisting of features such as slanted lines, dots, or cross-hatching because they create the uncomfortable illusion of movement. Also, don't use areas or volumes for data that are actually one-dimensional in nature. For example, don't use the drawings of dollar bills to represent budget amounts for different years. And never publish pie charts because they waste ink on non-data components and they lack an appropriate scale. It's very difficult to compare things on pie charts. Now, these were hitting some of the more frequently types of graphs that are used. There's a lot of different types of graphs, and especially with computers being able to create things now, there's a lot more that are easier and faster to be able to graph. Where's that example I wanted? I think that's the one. So sometimes you're going to see things that are a lot more complicated as we're doing this one. This one's a diagram of the causes of mortality in the Army in the East. And it's got lots of different information. It's got the blue is preventable or some sort of other type of disease. The red is wounds. The black is other causes. And so it's looking at separating things out. This one's really harder to see than I thought it was. It separates it out into a lot of different information. This was from Florence Nightingale that was creating these. And so creating different ways to show some statistics. Lots of different things to do, but obviously being able to read it and understand it is the most important piece that you want to make sure somebody else can look at and do. All right, homework then from both sections 2.3 and 2.4. Test looks like it's going to fall on February 6th. The project that we will be doing is going to involve needing to have an example of a bar graph, an example of a line graph, an example of a pie chart or a pie graph. Go ahead and start looking for those. They need to be actual true data, not somebody else that's just posted something on the internet. It was their own pretend information. I wanted something that's been published. So coming from some sort of reliable source. I guess it doesn't always have to be published. If you pulled something from a government agency that they may not have published, but publishing on the internet even would count for something like that. But a true agency or a newspaper article or something like that to where it is reliable information and not just, hey, here's a bar graph that my 4th grader made type of thing. So go ahead and start looking for those, and then I'll give you guys later on the questions that you'll answer on those. February 6th. Yeah. So you've got some time.